Hello, everyone. So this is Rubaiyat, and he's going to be talking about Anki and the Gramian Matrix. If you're watching on YouTube, please like and subscribe. Yeah, all right, I'll hand over now.
Yeah, sure. Okay, so hello everyone, and today we're going to be figuring out how to take the determinant of a rectangular matrix. As an outline for the talk, I'm going to do a quick recap of linear algebra concepts, and then we're going to build on those to derive this object called the Gramian or Gramian Matrix. After that, we're going to see how this Gramian can be used to encode shape. I'll explain what that means when we get to that. Then we're going to do a discussion about Anki and space repetition, all of that stuff. And if we have enough time, or if you want to stay, we'll see how you can generalize the surface integral formula using this Gramian object. Right. So first, just some stuff about linear maps and matrices. Linear map has two properties that it satisfies, additivity and scaling. Given bases EI and FA of a vector space, you can represent the linear map using a matrix M. So if you use summation convention here, you have L of EI is MAI times FA. And from that, you can derive a matrix vector multiplication form. So you get L of XI EI becomes that. So the eighth component becomes MAI XI, which you might recognize from your part 1A course in the matrices. It turns out that if you've got linear map from and to n-dimensional space, that scales n-dimensional volume, or sign volume, where you take into account orientation, by a constant. And that's called the determinant of that linear map. If you want to find that, what you do is represent the matrix by, represent the map by a matrix M, and then you just use some determinant formula, like expanding along columns, or a computer maybe. And then one useful property of a determinant is that it's multiplicative. So, okay, if one linear transformation scales stuff by 3, like scales area by 3, and another scales area by 7, then if you do them both in a row, it would scale by 3 times 7, 21. And you can prove this algebraically as well, but it's a bit more effort. You have to use like epsilons and summation convention and stuff. All right, I did say I made some animations for this talk, right? So I guess we should get started on that. And I was joking earlier, this is where the talk actually begins. Okay, so what's the first thing I talked about? Matrices can be used to represent linear transformations. Let's see what that means visually. So a linear transformation is one that keeps grid lines parallel and evenly spaced. By the way, just let me know if these animations are a bit choppy or something like that. I'm not sure there's much I can do to fix that. But yeah, so I'm just playing some examples of linear transformations here. So there's all these different weird linear transformations, but like there are also simpler ones, like a rotation, because after that, grid lines are still parallel and evenly spaced. So what we often do is write vectors in terms of these two vectors here, I hat and j hat. They're called the basis vectors. And they're called that because you've got a general vector v, you can write it as a linear combination of I hat and j hat. So here v is written as minus 2 I hat minus j hat. And these coordinates essentially are unique. It's basis. Then when you apply a linear transformation, the property that grid lines remain parallel and evenly spaced means that L of v is minus 2 L of I hat minus L of j hat. So it still has the same coordinates in a sense. There's still minus 2 times whatever I hat is now, and minus whatever j hat is now. So because of that, the transformation is entirely determined by where these basis vectors go. So what we do is we record the coordinates of where the basis vectors go. We put those into the columns of a matrix. The second thing I talked about was how the determinant can be used as a kind of volume or area scale factor. Why should we even have an area scale factor for linear map? Let's see. So I'm playing a linear map here where we start off with the unit square. And let's say that square turns into a parallelogram, its area gets scaled by a factor of k. It turns out this implies that all areas in the plane get scaled by k. And let's see why. Well, if I add in a bunch more grid squares, then because grid lines remain parallel and evenly spaced, all of these are similar parallelograms, right? So all of their areas would get scaled by the same factor, k. Then anything that's not a grid square, like the circle, can be approximated with grid squares. And if you use smaller and smaller grid squares, you can get a better and better approximation. So when you apply the linear transformation, and all of those small grid squares have their area get scaled by k, it kind of makes sense that the circle as well would get its area scaled by k. So now, what are we interested in? We're interested in determining the area of a parallelogram, or the 3D volume of a parallelepiped, which is like a 3D version of a parallelogram, or in general, the volume of a paralleletope, which is like an n-dimensional version of a parallelogram. So what do we already know? Well, what we know is that if you've got n vectors, which are all n-dimensional, you can form a matrix whose columns are those vectors, and then take the determinant of that matrix, or I guess the absolute value, if you don't care about orientation. If you're given two vectors in 3D space, then you can use this operation called the cross product, and then to get a third vector, which is perpendicular to both of them, obeys the right-hand rule, and also its length happens to be the area of the parallelogram spanned by those two vectors. What else? I guess technically, if you're given a single vector, you can find its length, which is like a one-dimensional volume, but that's not really, that doesn't really fit in. So let's see this part visually now. So here, I've got the grid, and I've got a unit square here, and we're going to transform this square into a parallelogram whose first vector is 2, 0, and whose second vector is 2, 3. So after the transformation, it has a base of 2 and a height of 3. So its area is 6. You can also think of it as, okay, you have this triangle here, you move it to this side, and you have a 2 by 3 rectangle. And that lines up with the determinant of that matrix having a value 6, or absolute value 6. And in 3 dimensions, we start off with a cube, and we're going to transform it into a parallelepiped whose first vector is 2, 0, 0, whose second is 0, 2, 0, and whose third is 1, 1, 1. So we apply the linear transformation. And you can see that, okay, so its base is now 2 by 2. And its height is a bit difficult to see from this angle, so I'll just change the angle here. And its height is 1. And that lines up with the determinant of this being 2 times 2 times 1 being 4. So the reason why both those examples worked is that we started off with a unit square, or a unit cube, whose area volume was 1. So then it gets scaled by the determinant. So its new area volume is 1 times the determinant, i.e. the determinant. Cool. We've also got this special case where you've got two vectors in free space and take a magnitude cross product. So we've got two vectors here. You have the parallelogram spanned by those two vectors. And what you do is compute the cross product vector and you take the length. So algebraically, if I tell you that V and W have coordinates 1, negative 2, 1, and 2, 0, 2, you can calculate that the cross product has those coordinates, negative 4, 0, 4. So the length of that would be root 32, which is about 5.66. So apparently, that's the area of that parallelogram. What about the general case? So here's what we're going to be tackling. We're given n vectors in d-dimensional space. So like, for example, we had 2 vectors in 3-dimensional space before. So there n would be 2 and d would be 3. what we want to compute is the volume of their n-dimensional parallelogram. So like, for example, if you were given two 5-dimensional vectors, they form a parallelogram, and that parallelogram has a 2D area, not a 5D volume. So we want to figure out that volume. And also, we're just going to assume that n is less than d, because if it's equal, we know you can use the determinant, where you make a matrix whose quantities vectors, the determinant. If it's greater, there's just 0. Like how if you have 3 2-dimensional vectors, then their 3D volume is 0, because they're all in the plane. This is a hard problem, because you can't just take the determinant. After all, that'd be like trying to take the determinant of a rectangular matrix. So let's look at a simpler problem. Is there a different way to do it for 2 3-dimensional vectors? Well, okay, we've got V and W there again. And we know you can figure out using the cross products, blah, blah, blah. But what we're interested in is there a different way to find the area? Well, if you stare at this problem for long enough, one idea you might come up with is this. Rotating everything into a low dimension. What do I mean by that? Well, I'll give you the coordinates of V and W again, 1, -2, 1, and 2, 0, 2. And the hope is that you can find a rotation matrix. How exactly? For now, we'll just say it's by magic. So in this case, the particular rotation matrix that works happens to have those values. I ran them to do 2 decimal places here. So you find the matrix by magic, and you apply the matrix, which rotates the vectors down to the xy plane. And then what we do is change our perspective. So what I'm going to do here is move the camera so that we're looking down the z-axis. And now, we just think of these as 2-dimensional vectors. You can see here that, okay, this parallelogram has a height of about 2, and its length is slightly less than 3. This area would be slightly less than 6. And that matches up with our early value of 5.66. What does it look like computationally? We've got V and W again. We've got our magic rotation matrix. We apply the matrix to V to get a vector, and you notice that its third component is 0, which means that it has no vertical component. It's like a 2D vector. So we put that into the matrix, removing this third component. That's what it means to regard it as a 2D vector. Then we do the same for W. And then you just take the determinant of this matrix. And that actually is 5.66. Because you think about, okay, AD, that's 0. BC, that's 2 times -2.8, which is about 5.6. So yeah, that does work out. So this is another way to think about it. But we found that rotation matrix by magic, right? And that's not really satisfying. We're not here to do magic today. We're here to do some mathematics. So how could we actually find that rotation matrix? Well, in higher dimensions, the analog of a rotation matrix is an orthogonal matrix. So if you remember from vector matrices, orthogonal one is one for which P transpose P is the identity. And technically, those include reflections as well, which might flip around the area. But that won't affect the size of the area, because we're not interested in the orientation. We're just interested in computing the absolute value. So we don't really have to worry about that. So the way we're going to get this orthogonal matrix is by doing a change of basis matrix between 2 orthonormal bases. If you remember, orthonormal means all the vectors have unit length, and they're all mutually perpendicular to each other. So let's say here we've got the blue basis and the purple basis. We're using a change of basis matrix. How exactly do you know that the matrix is orthogonal again? Well, because it preserves dot product. This is an alternative way to think about the condition for orthogonality. And you can go through the algebra for this. Okay, so P sends one basis to another, blah, 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 some Khondaker deltas. And because it preserves dot product between basis vectors, it preserves it in general, which you can prove using some linearity. But the basic idea is that, okay, the lengths of each basis vector don't change. And that's actually enough to say that it's an orthogonal matrix. So here's the plan. We're given n vectors in d-dimensional space, where n less than d. We're going to get a basis for the span of those vectors. Remember, the span of number of vectors is just the set of all vectors that can be written as a linear combination of u1 up to un. Then we convert that to an orthonormal basis. Then we're going to extend it to an orthonormal basis of the whole space. Then we're going to use a change of basis matrix from that new orthonormal basis to the standard basis. What exactly do I mean by the standard basis? Just those vectors there. So like I hat, j hat, k hat, l hat, essentially. Just those vectors there. All right. So let's see visually how you'd get a basis for this span. Here I'm putting three vectors in the plane, u, v, and w. And it turns out that u, v, w is a spanning set for the plane. What that means is that given any vector z, you can write it as a linear combination of u, v, and w. But note that you can write w itself as a linear combination of u and v. So you can substitute that into the equation for z and write z purely in terms of u and v. You don't actually need w. So z is in the span of u and v where you remove w. And actually in general, the entire plane is in the span of u. So u and v by itself is a spanning set for the plane. And as you see here, u is actually I hat and v is j hat. This actually forms a basis for the plane. So the general idea is, okay, u1 up to un works as a spanning set for the span of u1 up to un. It's like just true by definition. Then, if it's linearly independent, we've got a basis for their span. By definition, it's a basis if it's linearly independent and it's a spanning set. If it's not linearly independent, you can express one of these vectors here in terms of one of the others. Like how you could have expressed w as, I think it was 2u plus v. So you can throw that vector away while still preserving the span, because you could just substitute the linear combination, like how you could substitute w equals 2u plus v into the z equation. You can substitute it in general. So you just keep throwing vectors away until you found a basis. Okay, cool. So we know it's find a basis. How would you convert it to an orthonormal basis? So here we're going to use something called Gram-Schmidt orthonormalization. Let's see a visualization of this. We've got two vectors here, which work as a basis for the plane. Normalize one of them. Remove parallel components. Note they're now perpendicular. You just normalize a second. In general, okay, how does this work? So you've got your basis u1 up to uk now, where I might like rename some of the vectors to make sure it's a really independent set. Then you normalize the first vector, like how you normalize the green vector at the start. And then you just repeat this algorithm. You remove the parallel components, which turns out you do via this dot product thing, and then you normalize. And you just keep going until you get to UK, and then you've got an orthonormal basis. Cool. Okay, so we can get an orthonormal basis. So now let's see, how would you extend this to a general orthonormal basis of the entire space? Well, we've got V and W there, and their span is that plane, which I've just rotated there. What you do is you added the standard basis. So here that's I hat, j hat, k hat there. If I rotate this vector, you can see that the blue and purple vectors aren't in the span because they don't lie in the plane. It does turn out that the yellow vector is in the span, which you can see by actually finding a linear combination of the green and red vectors that work. So if you wanted to extend the green and red vectors to a basis, you would add either the blue vector or the purple vector. Because, okay, that allows you to reach more vectors. In general, okay, you've got your basis, which has been orthonormalized. You see which of the standard bases, so 1, 0, 0, 0, 1, 0, blah, 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 is not in the span of U1 up to UK. And here's the thing. If they're all in the span, then you've actually found the full basis, because you can represent any vector in terms of the standard basis, and you can represent any standard basis vector in terms of U1 up to UK, which means you can represent any vector in terms of U1 up to UK, so it's a basis for the whole space. So you have that we're happy. Otherwise, you just add one of the standard basis vectors that's not in the span, and you just repeat from this line. And eventually that will let you get a basis of the whole space. And you can just apply Gram-Schmidt again, essentially, to get an orthonormal basis. And now I'm just going to justify that something which I had glossed over, which is, okay, why does this actually rotate them into a low dimension? Well, okay, let's say got U1 to UN as a spanning set. We find a basis as a subset. So if you remember, the dimension theorem says that the dimension of a vector space is just the number of vectors in any basis of that space. So the dimension of their span is at most n, because we can find a basis as a subset of this. So we'll have at most n vectors in it. So when we do a change of basis, we only use the first n standard basis vectors to describe them, just like how when we rotated down to a low dimension before, we only used I hat and j hat to describe BMW. The k hat component was 0. And so only their first n components could be non-zero. All the rest are going to be 0. So they really are now basically n-dimensional vectors. So what might this look like in code? And like the reason I've been going through this in so much detail is because we're actually trying to compute this. You could always say, okay, let f be the function that, given n vectors in d-dimensional space, spits out the volume of the parallelism. It's not really that useful if you can't actually compute it, right? You can always define a function. That's me. So here's what it looks like. So I'm just writing this in Python. So I'm just using a trick where you basically take the length of the first vector as that's the dimension of the space. And what that means is that you know that the identity matrix has columns 1, 0, 0, 0, 0, 1, 0, 0, and so on and so on, which those columns are just the standard bases. So that allows you to get them. So what we do is that we turn the vectors into a basis, then we orthonormalize them. Then we start off with our orthonormal basis just for the span. We extend it to one of the full space by using the standard basis as our spanning set to add vectors in from. Then after that, we orthonormalize it. And then our orthogonal matrix is going to be the change of basis matrix. So we apply the orthogonal matrix to each vector. Here I'm just using like a list comprehension in Python. I'm not sure if you've seen that before. Then we remove those trailing zeros to make them n-dimensional. And after that, you return the absolute value of the determinant of the matrix formed by those vectors. So this is all the code. Well, it's not all the code. It's like one function from the code. And you know, this code is just all kinds of terrible because it's very long. You have to, I haven't implemented these auto-normalize and make basis functions, so you'd have to figure out how to do that. Like, okay, how do you actually figure out if a set of vectors is linearly dependent? Like, how would you figure out, okay, if you've got 5 7-dimensional vectors, how would you figure out if that's linearly dependent? Because you'd have to like solve a matrix equation maybe. And okay, how do you actually figure out if one of the standard bases is in the span? Again, that's solving a matrix equation. You have to figure out, okay, how do you compute the change of basis matrix? It's just very, very long, very, very tedious. So can we do better? Well, let's analyze the algorithm a bit more closely this time. Starting with our vectors. Here, I'm just bringing back the example in particular that we did. So 1, -2, 1, and 2, 0, 2. Apply the orthogonal matrix. And now this time, we didn't find it by magic. We had to go through that whole process to find it. Then we drop the trailing zeros. And here, I didn't drop both trailing zeros because we're just making them 2D vectors. We're not making this like a one-dimensional vector. And the point is that we can form a square matrix from these new vectors. Because we've got n vectors, which are all n-dimensional. So it'd be an n by n matrix. And the good thing about square matrices is that we know how to take their determinant. Yeah, so that's how that works. What you might notice is that from the first step to the second step, dot product between any two vectors was preserved. Because after all, we applied an orthogonal matrix, and orthogonal matrices preserve dot product. From the second to the third step, we also have dot product preserved. That's because, well, removing trailing zeros won't affect the dot product, right? You just have, okay, 1 times 8, 4 times 5, 2 times 7, then 0 and 0 at the end. That won't contribute anything. So, we have this very useful identity that ui.uj is always equal to wi.wj. So now, let's consider the matrix U whose columns are the ui. So in our particular case, that would be this matrix right here. 1, -2, 1, and 2, 0, 2. And the matrix W that we had these numbers here. Then, the clever step is to consider W transpose W. So here, remember the transpose is where you just flip the matrix along its main diagonal. That gives you a matrix whose columns are, whose entries are 6, 4, 4, 8. And it turns out that because of this property, that's equal to U transpose U. Like for example, if you think about that top left entry there at 6, you compute it by multiplying together this first row and this first column, right? Which is like taking a dot product of this row and this column, i.e. this dot product, this taking the dot product with itself. Now here, you're doing a similar thing, where you're doing, okay, this row times this column is like this column dot this vector here. So they're equal because of this property. This is like, this entry is like w1.w1, and it's also u1.u1. And then, for example, this entry would be, so this first row, second column, that would be w1.w2. It's also u1.u2. Those are the same. So we have w transpose w is u transpose u. And the great thing about this is that you don't need to figure out what the orthogonal matrix is to compute u transpose u. You just need to know the vectors, and you are given that information at the start. So what we do is that we take determinants on both sides. Now, we can't break up that right determinant because U was a rectangular matrix, right? Like, for example, here, we can, if you try to do the determinant of this, we wouldn't be able to break it up as det U times det U transpose, det U transpose. The good thing is that W is a square matrix. So we can break up that left factor as delta W transpose times that W. Then what you do is use the fact that the determinant of a transpose is the same as the original determinant. The det W squared is that of U transpose U. So you take square roots on both sides, and you get that the absolute value of det W is the square root of the determinant of U transpose U. What's amazing about this is on the left side, we have the volume, right? Because the volume is the determinant, except of course we don't care about orientation, so we take the absolute value. And on the right, we have something that's very easy to compute. None of that magic orthogonal matrix stuff. So if you look at the code for this, it's this short. And this code actually works. You don't have to define orthonormalize or whatever like that. It's just this. It's basically a one-liner. I just separated it out a bit so that you can see it a bit more clearly. But if I wanted to, I could put this all in one line. And that's amazing because remember, previous monstrosity we had was, how big was it? It was this big. And now we reduced it to something which is this big. It's pretty good. Now, before we go on, it's useful to think about, okay, why did that actually work? Why were we able to simplify it down so much? Well, the first step was reducing everything to a known problem. The known problem there was, okay, we know how to take the determinant of a square matrix. So let's try to get to there somehow. The thing that really helped was that we exploited the invariance of the dot product. What that allowed us to do is forget about how we got from the start to the end and just focus on the start and the end. Right. So let's go through an example here. So if you actually compute the gradient here, it has entry 6448, as you've seen before. You take the determinant of that matrix, and it's 32, because 6 times 8 is 48, and 16 is 32. And that's 5.66 squared. That's the square of the parallelogram area. So it does actually work. We're not crazy. At least not here. Okay, but we know that there's another way to figure out the area of the parallelogram using this cross product magnitude. So is the Gramian actually consistent with that? So it turns out it is. You do need to know some triple product formula to prove these. So you have A dot B cross C is B dot C cross A, and also A cross B cross C is A dot CB minus A dot BC. So if you remember those, then you can actually try to compute, okay, what is A cross B dot A cross B? Well, it turns out it's equivalent to this. Basically what I've done is bring this A to here, this B to here, and this A cross B over to there. So we had capital A dot capital B cross capital C is capital B dot capital C cross capital A. Then we use the triple product formula. Then we distribute the dot product, and hey, that's a determinant. So it is consistent because this here would be the square of the length of the cross product, which would be the square of the parallelogram area. And this Gramian determinant is also the square of the parallelogram area. So nice, math is consistent. Very good, very good. All right, but I said today we're going to learn how to take the determinant of a rectangular matrix. We've sort of done that, but what I want to make here is make the connection more explicit. So what transformation does this rectangular matrix represent? Well, remember, when we represent a linear map by a matrix, this first column is where I hat goes. The second one is where j hat goes. So what this is a transformation from 2 dimensions to 3 dimensions. And let's see that visually. So we start off in 2D with the plane. There's I hat and j hat there. But we're going to end up in 3 dimensions. And those are where I hat and j hat are going to end up. So remember before, I said that a linear transformation is one where grid lines remain parallel and evenly spaced. And it turns out that that's still true. It's just that they happen to be parallel now in 3 dimensions. And they're evenly spaced in 3 dimensions. And the great thing about that is that we can play the same determinant game. So, okay, we've got a unit square. Then we apply the transformation. It gets morphed into this rotated parallelogram shape. And its area gets scaled by a factor of k. Then we can add in a bunch of other grid squares of varying sizes. And then because grid lines remain parallel and evenly spaced, these are all still similar parallelograms, even if they're now rotated in 3D somehow. So all grid squares get scaled by a factor of k. And if you do a circle, well, you can approximate a circle with grid squares, and you get better and better approximations for smaller and smaller grid squares. So when you apply the transformation, all of those small grid squares get their area scaled by k. So the area of the circle also gets scaled by k. And in fact, we have an arbitrary region would have its area scaled by a factor of k. So when we computed the Gramian of this matrix here, and then took the determinant, and then took the square root of that, that 5.66 represents an area scale factor. It just happens to be an area scale factor for a transformation from 2 dimensions to 3 dimensions. So we have something which I'm calling, what I like to call the linear volume scaling theorem. I'm not sure if this actually has a name, which is like a template name. And it's that if you have a linear map from n-dimensional space to d-dimensional space, and here we're not using the restriction that n could be less than d. N could be equal to d, it could be bigger than d, we don't really care. Then we have the remarkable property that this always scales n-dimensional volume by a constant. Always. If you want to actually compute that constant, well, if they're equal, we use a determinant. That's what we've done before. If n happens to be less than d, we can use this square root of the Gramian determinant. So it sort of works as this generalized determinant that also works for rectangular matrices. If n is bigger than d, it's 0, it's squishing to a low dimension. Just like how, okay, if you've got a transformation from the 3 dimensions to 2 dimensions, then all volumes go to 0. Just squishing it down into the plane. All right, so we've been focusing on the Gramian determinant, but now what we're going to do is focus on the matrix itself. What is the Gramian matrix? It's that matrix of dot products. It's what you get when you do U transpose U. So remember, okay, the top left entry was the first vector dotted with the first vector. What you might notice about this matrix, that it's invariant if you apply an orthogonal matrix to A, B, and C, like if you apply a rotation or reflection. Because after all, what does an orthogonal matrix do? It preserves dot products, the entries of dot products. But actually, it turns out something stronger is true. They give you like these 6 random vectors. It turns out they have a common Gramian. Like if you form the matrix with columns of those vectors and do, okay, M transpose M, it computes for the same Gramian. And what that means visually is that you can rotate one set of vectors into the other. So how would you actually prove this? So what we're going to prove here is that, okay, if 2 sets of vectors have the same Gramian, then you can apply an orthogonal matrix to one set to get the other set. So, okay, we've got U1 up to UN, V1 to Vn in d-dimensional space. Here, we're not going to assume that n is necessarily smaller than d. It could be equal to d, it could even be greater than d. And this is what we know, that ui.uj is the same as vi.uj. What we want to say is that, okay, let's just rotate them down to n dimensions and then use a change of basis matrix. Like, okay, if you've got one set of 2, 3 vectors, another set of 2, 3 vectors, both of which have the same Gramian, you just rotate them both down to 2 dimensions, and then use the change of basis matrix. The problem with that is that these sets of vectors might be linearly dependent. So for example, if you've got 3 2D vectors, then they're definitely linearly dependent. Say we've got U1, U2, U3, and also V1, V2, V3. Now these all have the same Gramian because you can rotate one set into the other. And remember, the Gramian is invariant on the rotation. But they're linearly dependent. You can't just say, okay, let's change from the basis U1, U2, U3 to the basis V1, V2, V3. Because, well, this is not a basis. So the way you fix that is this idea of corresponding linear relations. So let's unpack that. A linear relation, if you remember, is just a linear combination of vectors that's equal to the 0 vector. So for example, if your set of vectors is a basis, then the only linear relation is what's called the trivial one, where you set all the coefficients to 0. That's like another definition of linear independence as a linear dependence. So, and you've got this important identity here. Ui dot uj is the same as vi dot vj. Okay. If you have a linear relation among the ui, that's the same as saying that if you dot this vector with itself, you get 0. The reason for that is that a vector is a 0 vector if and only if its length is 0. And you compute the length of a vector by doing the dot product with itself. I'm also just going to change the I here to a J. Might be difficult to see, just because that will avoid some collision in notation a bit later. So we expand that using the linearity of the dot product. And then we use our key property to convert this into sum over lambda I times lambda j of vi dot vj. And that's the same as saying that sum over I of lambda I vi is 0. We just retrace our steps. So this is what I meant by corresponding linear relations. That if you have a linear relation among the ui, it will also work for the vi, and vice versa. Let's see what that means geometrically. Here we've got u1, u2, and v3 again. And now I'm not going to draw v1, v2, and v3. You might notice here, okay, you can write u3 as u1 plus u2. But you can convert that into a linear relation by just subtracting. And so, by the corresponding linear relations property, which says that if you have one for the ui, it also works for the vi. We know that this necessarily means that v3 minus v1 minus v2 is also 0. That's the corresponding linear relation. So v3 is also v1 plus v2. And if you actually go back to what v3 looked like, you can see here, yeah, that works. v3 is v1 plus v2. But the great thing about that is that we deduce that without having to actually look at v1, v2, and v3. So here's how to find that orthogonal matrix. So you take u1 up to un, and you find up to k as a basis for the span. Then it turns out that that implies that v1 up to vk is also a basis. And why is that? Well, if u1 up to uk is linearly independent, that means that their only linear relation is the trivial one, where you set all the coefficients to 0. But because of the corresponding linear relations property, that means that the only linear relation among v1 up to vk is also the trivial one, where you set all the coefficients to 0. So it's linearly independent. And as for being a spanning set, well, if you go back here, u1 and u2 work as a spanning set. You can write u3 in terms of them. And because, again, of this corresponding linear relations property, that means that v1 and v2 also work as a spanning set. You can write v3 as that same linear combination. So v1 up to vk is also basis. So all you do that you rotate them both down to k dimensions, and then use a k-dimensional change of basis matrix. Technically, you'd have to also fix the other standard basis vectors to make it a fully d by d square matrix. But that's just like by the by. So this is what I meant when I said you can use the Gramian to numerically encode shape, because it's a way to encode vectors as independent of rotation and reflection. Because if you have vectors with that Gramian, then if you rotate them or reflect them, that doesn't change the Gramian. And also, if two sets of vectors have the same Gramian, then you can rotate one into the other. It's like an if and only if. But if you actually take a look at the entries of the Gramian, this makes a lot more sense. Because what are the entries? Well, they're basically the lengths and angles, right? I mean, the diagonal entries, okay, this is the length of A squared, from which you can figure out the length of A, length of B, length of C. And once you know the length of A, B, and C, you can figure out, okay, A dot B, that's, okay, length of A times length of B times cosine of the angle between them. So you can use an inverse cosine stuff to figure out the angle between A and B. So actually, if you know the Gramian matrix, you know all the lengths and angles between your vectors. And vice versa. If you know the lengths and angles between your vectors, you know their dot products, so you can compute the Gramian. So what we've shown here is that lengths and angles determine shape. If you're given a list of vectors, you're given, okay, this vector has length 10, this vector has length pi, this vector has length 3, and you're also given the angle between any pair of vectors, it turns out that determines the shape of those vectors in n-dimensional space, up to a rotation or reflection. But what I don't think is obvious, and or at least I don't think is just immediately obvious, hopefully I've made it feel like a bit more intuitive, is that the determinant of this matrix has anything to do with the volume of that shape. Like, okay, sure, you can get the lengths and angles, but why would you think to arrange them in a matrix like this? And then why would you think to take the determinant of that matrix? Okay, so what else can you use the Gramian for? You can use it to compute dot products in not necessarily orthonormal bases. If you've got, okay, a linear combination of both, the formula there is x transpose times g times y. And this generalizes the usual formula. We have, okay, x dot y is x transpose y. That actually only works if you write your vectors in orthonormal coordinates. And that corresponds to, if you look at the Gramian, if your A, B, and C are orthonormal, then these entries here are 1, 1, and 1. And the off-diagonal terms are 0, 0, 0, 0, 0, 0. It's the identity matrix. So here you'd have x transpose iy, i.e. x transpose y. Oh, and by the way, because it's used to measure dot products, which is also used to measure length and angles, this matrix is sometimes called a metric matrix or a metric tensor, which you might have heard of. Like you use it in general relativity, for example. So the useful thing about this is that if you think about, okay, what's x transpose gx? That's just the length of a vector in some basis squared, which is always bigger than or equal to 0. So because x transpose gx is always bigger than or equal to 0, the Gramian matrix is positive definite, or I guess positive semi-definite. Maybe there's a vector which is equal to 0, which is not the 0 vector. It's also a symmetric matrix because, well, the dot product is symmetric, right? So A dot B is the same as B dot A. So you think the transpose will be the same. So Gramian is a positive definite, or semi-definite, symmetric matrix. But again, it turns out something stronger is true. If you let M be a real valued symmetric positive semi-definite matrix, then you know by the spectral theorem, which you'll have covered in vectors and matrices, that you can diagonalize M by an orthogonal matrix P, so one for which P transposes B inverse. Because it's symmetric, we know it has real eigenvalues. Because it's positive semi-definite, we know it has non-negative eigenvalues. You think of that as, okay, if x here was an eigenvector, then gx would be lambda x. So you have x transpose lambda x, which is lambda mod x squared. and that has to be bigger than or equal to 0, which means lambda must be bigger than or equal to 0. So what you can do is if you write U as P square root D P transpose, where when you take the square root of a diagonal matrix, you just take the square root of the diagonal entries. And you're allowed to do that because they're all non-negative. Then you have that U transpose U equals M. And what that means is that M is a Gramian matrix. And the vectors for which it is a Gramian matrix are precisely the vectors described by U. So, again, not only is every Gramian matrix a real symmetric positive semi-definite matrix, but also every real symmetric positive semi-definite matrix is a Gramian. In other words, it represents some shape. Let's go through, a particular example. So we've got this matrix G here. You diagonalize it. You take the square root of that diagonal matrix. We just take the square root of this, square root of this, square root of this. So our U there would be those. So then if we plot those vectors, then what we're saying is that this matrix here represents the shape of these vectors in space in such a way that doesn't depend on how you rotate or orient them. Right. So, does anyone have any questions? Just like this is like the first part to talk over. I just want to know if anyone has any questions. So, okay. Hope you enjoyed those promised animations. Oh yeah, this part at the start was just to troll you guys essentially. But yeah. Time for the second half. So, we know that the Gramian works for parallelopipeds, like parallelograms, parallelepipeds, and general. What about a general shape, like a sphere, for example? If I took a sphere and I applied some weird nonlinear transformation that took it into 4 dimensions, I can write, okay, x1, x2, x3, x4 in terms of x, y, and z, for example. Then what would its new volume be? It feels like we have enough information to figure that out, right? If we know exactly what the transformation is, we should be able to figure out the new volume. And the way you might imagine doing that is doing some sort of integral, right? But that would require somehow integrating over a 3D region in 4D space, like a kind of 3D surface integral, which is a bit weird. We don't know how to do that. We only know how to do line integrals. We know how to do 2D surface integrals. We don't know how to do 3D regions in 4 dimensions. So here's the plan. We're going to recap integration and change of variables in 1 dimension. We'll see how to extend this to 2D area integrals. Then we're going to see how to extend this to generalized surface integrals. By generalized, I mean, okay, you'll be able to integrate over a 2D surface in 4 dimensions, or a 3D surface in 7 dimensions, or a 10-dimensional surface in 42 dimensions, or however you want. Actually, hold on for a bit. Before we get into the maths, what you might notice is that I've been recapping previous concepts a lot. Like I went over, okay, why is it the case that you can take a basis as a subset of a spanning set? Why is it the case you can extend the basis to a full thing? And that's stuff you have covered in lectures, but I still decided to recap it. The reason why is because, well, maybe it's just I hope that makes everything easier to follow, right? It's not really a fun experience, like getting lost during maths talk and not having to just sit there till the end. That's because maths is pretty cumulative. Like, okay, if you're chugging along learning some maths, but you suddenly miss one concept or one thing just doesn't quite click right for you, what that can mean is that everything else suddenly becomes much, much harder. Even if you'd known that thing, it would actually be much easier. So it might not be that this later material is hard in and of itself. It's just that you forgot an earlier step and everything else became much harder. And maths is particularly susceptible to this. So usefulness of an explanation to you as a listener doesn't just depend on how good I am at explaining things, right? It also depends on your previous knowledge, previous understanding of that knowledge, but also your ability to recall that knowledge in the heat of the moment, right? Like if you, I mentioned the spectral theorem, for example. If you vaguely remembered that, but maybe it took like a minute for you to fully appreciate it, but it's not like I spend a minute on that whole thing, right? I just keep racing past and get the result I want. So if you can't recall it quickly, then it becomes a bit harder to follow, and that can have a big compounding effect. So there's only so much I can do as someone explaining the material. So as learners, because we're all learners here, we're all students, what can we do to help make explanations feel clearer to us? And here, so actually, again, I lied. We're not actually going to the second part. Well, we are going to the second part, but it's not maths. Instead, we're taking a slight detour into some cognitive science. Because we want to see, okay, how can we actually make sure explanations feel clearer to us? So, first of all, what doesn't work? Rereading, or at least just reading. So, there was a 1966 study by Tolving, where basically he gave two groups of people lists of English nouns, and then after some time, after they read through them for a bit, they were given another list of nouns and said, okay, you now have to memorize this list. Half the people were given the same list, and half of the people were given a completely different list that they hadn't seen before. So half of them already had an advantage, or so you'd think. But actually, when they did the results on the test, the results between the two groups were indistinguishable statistically. So here, rereading, prior exposure to the material, didn't actually help them in scoring better on the test. What helped was them saying, okay, we actually have to get a test on this now. We have to focus on it. We know we have to memorize it. This is something psychologists call the testing effect. It's the idea that testing makes learning stick far better than just rereading material. And that's why, for example, we do tons of example sheets, right? Because practice questions are a form of testing, and that helps the material stick in our brains. That helps us understanding better. There was like a 2010 New York Times report on this, where they did a study where they had two groups of students who were given a text to read. One group was immediately tested on the text after they reread it. They just had one test. And another group weren't tested it at all. Then what they found was that a week later, the students who'd been tested on the text immediately after they read it retained like 50% more of the information than those who had just read it. And that was all from one test, and that's after a whole week. So testing does not necessarily have to mean exams. It can mean like flashcards, quizzes, again, practice questions. It doesn't necessarily mean, okay, let's do exams every week now. But a natural question you might ask is, okay, how often should you test? Like, okay, should you test once every semester? That's probably too long. Once every month? Maybe once every week? Once every day? Probably not. So how often should you test? This is the part which most people don't seem to know about, the forgetting curve. So there was a German psychologist called Ebbinghaus, who all the way back in 1885 was the first one to do this. And psychologists have been pulling these curves for a while. There was like a recent replication of this in a 2015 study, I think. And the idea is that when you first learn a piece of information, your retention of that information, which is the ease with which you can recall it, decays exponentially. So maybe after like a week, you like remember like a very small amount of it, maybe like 30% or something. But if you test yourself on the information and review it, that decay slows down. So you don't have to test yourself every day. You do, okay, one day, and then wait 2 more days, review, and wait 3 more days, review. You can space out your reviews. And that's what psychologists call the spacing effect. The trouble with that is, okay, how do you actually plan around all of that? Because you can say, okay, so you've got like 8 topics, like per lecture course, maybe it's like as an estimate. That's what, 32 topics, and you have to individually keep track of, okay, so tomorrow I'm going to be reviewing this, this, and this, and then I have to change the intervals for those, and say, okay, next week I'm going to have to review this and this and this, and it just becomes a nightmare to manage. So it might be useful, but how do you actually implement it? It turns out the way you do it is that you let a computer do it. So this is where we get to Anki. Anki, well, it's a free open source flashcard program that combines the testing effects and spaced repetition, spacing effects. So the way it works is that each card has an interval, which is the time between reviews of that card, and a multiplier. So I made just this little diagram here. So what you do is that you review the card. If you get it correct, you do the interval times the multiplier. Let's say if the interval was 10 days and your multiplier was 2, now you become 20 days. If you got it incorrect, however, the interval resets. So I think the default value is like 1 day, and the multiplier goes down. So if it was times 2 before, it was now times 1.9. So cards you get wrong, you'll see slightly more often. And okay, so sure, you can have Anki as a thing. How do you actually use it for understanding mathematics? You might have heard, okay, med students use Anki a bunch for memorizing anatomy and stuff like that. What about mathematics? There's an obvious use case. You know, memorize definitions and theorem statements. I do want to emphasize that that's still important. It's difficult to understand a piece of text if you can't understand the individual words in that text. It's like trying to read something in a foreign language. A less obvious use case is memorizing explanations. And that could be proofs. It could also just be, for example, like just good intuitions to have, key insights. So to see what I mean a bit more by this, you have to go for the idea of, okay, Anki somehow makes memory a choice. This is from Michael Nielsen's Augmenting Long-Term Memory. So if you see something like, okay, this is a good intuition to have about this concept, you think, okay, I want to remember that for the future, but you can just plop that into Anki. Or if you think, okay, this definition seems pretty important, I want to make sure I remember for later, again, plop that into Anki. So a useful way to frame Anki is as a way to just say, okay, whatever I put into here is stuff that I'm pretty much guaranteed to remember later on in the future. So, of course, there are many different ways to make flashcards, and there are some ways which don't seem to help. So another guiding principle that you should use when using Anki and other flashcards is this idea of the minimum information principle, or the principle of atomicity. Basically just breaking down ideas into small pieces. Like, for example, if you're putting a proof into Anki, for example, you don't just have like one card for all of the proof. That's like way too much information to recall. It's going to be very difficult to remember that on the fly. So you might have, okay, different steps of the proof. Say, okay, why does this step imply this step? Ideally, each card will represent like a single idea. They're saying, okay, why is it the case that pure symmetric matrix is diagonalized by an orthogonal matrix, for example? And it doesn't necessarily mean it has to be simple ideas, for example. You can use like complex terminology, like math terminology, but it should try to be something that doesn't have too many pieces of information on one card. I've personally found that this helps to pinpoint areas of confusion. Like, for example, I'll have proof cards where I'll be given some steps to the proof and I have to fill in the next step. And if it takes me a while to figure out, okay, what is the next step? And then I see the next step and say, okay, yeah, that was the next step. And that's probably an indication that I don't actually understand the proof at that step. So I should try to revise that step a bit more and see why it's true. Maybe add some more cards because of that. So this is the specific model I use. I basically have two different kinds of cards, where I have definitions or short explanations for a regular flashcard, and also some longer explanations, where I have basically one card for each step and also one card for everything. I have like a custom template in Anki, which makes it like not completely terrible to make. You can actually, okay, a 7-step proof, you have to have 8 cards. It's terrible. And just one example of where this is useful to me. So 3.1 Brown made like a really good video which illustrates the properties of the cross product. Like, okay, why is it the case that if you take the cross product, take the magnitude, and that's equal to the area of the parallelogram? And why is it also perpendicular and obey the right-hand rule? It's a very good video. And I must have watched this video like at least 5 times. over a few years. And each time I watched it, off the video, I felt like, okay, yeah, this is a very good intuitive explanation. I really feel like I understood this. But what always happened is that after a few months, and I try to remember it again, but I just forgot all the details. And because of that, I didn't actually really have that good intuition for the cross product. I just remembered, okay, yeah, I remember that it's supposed to be perpendicular, and it's supposed to have the length equal to the area of the parallelogram, and it's supposed to obey the right-hand rule. But I don't remember why. And I remember that, okay, there is some geometrical intuition for this. Again, I didn't actually remember the intuition. It's only really after putting the explanation into Anki that I actually managed to solidify my understanding of the cross product. There are some caveats here. Well, again, as I said, we're not doing magic today in the talk. So the specific design principles of Anki haven't necessarily been justified scientifically. Like, okay, your cards start off with an interval of 1 day, and it goes to 3 days, and then 7 days, and stuff like that. Like that particular pattern hasn't necessarily had experiments done on it and like justified. Or like, okay, at the start you multiply it as I think 2.5 times, and then the specific way in which the multiplying decreases. All of that stuff is heuristics, which Anki developers have chosen. But the alternative is either, okay, we wait like what, 50 years or something for all the results to come in, or we become psychologists ourselves and try to understand all of this. And I like Anki, I like space repetition. That doesn't mean I want to become a psychologist. So what we do is we just do the best with current science that we have, i.e., we know that the testing effects and the spacing effects are real phenomena. So let's see, okay, what are the ways in which you might be able to incorporate that into something like Anki? Okay, so as a summary, the usefulness of an explanation can be affected by the learner's recall, recall of their knowledge and their understanding, and also how easily they can do that. In terms of improving that recall, it's better to test rather than just reread of the same thing over and over again. And the spacing effect means that you can do this really efficiently because the intervals increase exponentially, right? It's like times 2.5, times 2.5, times 2.5. You get very long very quickly. Anki, because it manages it all with a computer, is a useful way to implement it. And the main ideas for using Anki are keep in mind that you're trying to make memory feel like a choice rather than something that you just say, okay, I hope I remember this. And also this idea of the principle of atomicity. Okay, just like a small plug, I wrote this a plugin called Obsidian to Anki, which basically I keep notes in this text editor called Obsidian. And it allows me to put them into Anki. So you don't have to like copy paste everything into there. See all the link on there. All right, now let's actually go on to the second part of the talk. All right, so yeah, as before, we worked with parallelopipes, one about general shape. And then we've got this plan where we're first going to go over integration, hinge variables in one dimension. And then we're going to see how to extend that to 2D, and then see how it extends to generalized surfaces. All right, so first, integration in one dimension. You've got this function f of x, and we're trying to figure out the integral of it, which you can think of visually as the area under some graph. The way we figure out that area is that we approximate it with a bunch of small rectangles. And those approximations get better and better if you use finer and finer rectangles, because it captures more properties of the shape of the graph. So if you write, for example, a substitution, x equals 2u, and the graph gets transformed like that, and the integral gets transformed by something. And we're just going to go over, okay, what is this actual something? So what we're going to do that is we're going to relate approximations in the u world with delta u. So those in the x world with delta x. So you've got this interval, 0 to 1 f x dx. We'll split into 3 parts: the domain, the integrand, and the width element. and we make the substitution, x equals 2u. So we know how the domain changes, which is 0 to a half now. And we know what the interim changes, which comes out to 2u. We know what the width, and well, the width element is the thing that we're going to focus on. So if we do a substitution like x equals g of u, then the way we're going to think about this is as a mapping from u to x rather than the other way around. It just turns out that this particular way of thinking about it simplifies some of the algebra later on. So what we're going to do is we're going to construct a u integral that's equivalent in a sense to the x integral. Like for example, for the domain, well, for example, x equals 2u. Feeling that as okay, you transform the domain by applying g inverse, which is multiplying by a half. Another way of thinking about that is okay, you have your target domain here, and you're applying g here. You're wondering, okay, what's the equivalent domain then? Okay, so we've got x equals 2u. We're mapping from u to x. And this transformation here is linear. In this case, in one dimension, linear means evenly spaced dots remain evenly spaced. So any width gets transformed to twice the width. And that's the correct width in the x world. And in general, okay, so the width is delta u. So 2 times delta u becomes delta x. That 2 there is like a correction factor. That makes the width in the u world equivalent to the width in the x world. What about something else, like for example, x equals u squared? Well, when we apply this transformation, it's definitely non-linear, right? Because the width doesn't remain the same. Like, evenly spaced also remain evenly spaced. But what we can do is zoom in around a particular point. So here I'm zooming in around 3/4. And watch what happens in this square here. It looks pretty linear around here, right? It looks like a scaling by about 1.5. So this is the original position, so this is about 1.5, then from 2 to 3 here. And actually, that's what it means for the derivative at 3/4 to be 1.5. It means that, okay, change in x is about 2u change in u, so 2 times 3 to 7.5, 1.5. And so even if it's not linear, it has this property of being locally linear, which means that if you zoom in on a particular point, like 0.75, the transformation looks linear. So, near a particular point, you've got, for example, in that example, we had a width there went to about 2 times 0.75, i.e. 1.5 times the width, which is the correct width. And in general, around a general point here, u, a width near it would go to about 2u times the width. And that 2u there is again working as a correction factor. That's a sort of width distortion factor near that point. So in general, let's say, okay, you got a substitution, x equals g of u, and change in u goes to g prime of u change in u, i.e. change in x. You've got the width, the correct width. You've got the local width distortion factor. And technically, it's not equal to, well, it's an approximation, and that's because we were only at a finite zoom level before. Like here, when I zoomed in to 3/4, for example, I didn't zoom in infinitely far, I zoomed in finitely far. So it's only going to be an approximation. The way we fix that is essentially just changing these changing u's and changing x's into differentials, du's and dx's. And that is basically just the integration by substitution formula in one dimension. So now let's see how you can extend this to 2D area integrals. So we've got 2D change of variables. We're only going to focus here on how the area element changes, because again, it's pretty easy to figure out how the domain and the integrand change. So we write xy as functions f1 of uv, f2 of uv. And again, we're thinking of this as a mapping from uv to xy. And it's generally nonlinear. Like, for example, if you write xy as r cosine theta, r sine theta, that's a nonlinear transformation. And there's all sorts of different nonlinear transformations you can do to the plane. But if you zoom in on that transformation I just played, and remember that in 2D, what it means to be linear is that grid lines remain parallel and evenly spaced. Zooming in on this particular point, the focus here, then it doesn't really look linear. They still look curved, right? But maybe we just didn't zoom in far enough. So I'm going to zoom in a bit closer. And that might look a bit more linear. It still looks a bit curved, slightly more linear. And if we zoom in even closer, that looks pretty linear now, right? They look parallel, they look pretty evenly spaced. What I've done here is that I've centered our position on that point, which was at coordinates 1.5, negative 0.5. I'm going to go through various zoom levels of the transformation. And we might notice is that it's getting more and more linear each time. And this looks pretty linear now, right? It looks like pretty straight lines and they look pretty evenly spaced. Okay, so it's linear transformation. How would you find the matrix representing it? Well, normally what you do is follow the basis vectors, right? That's what we did right at the start of the talk. But they actually turn out to be too big here. Because we're zoomed in times 500. If I actually try to draw the basis vectors here, they're like really, really big. It's like not really practical to follow them. Instead of what you do is consider really small vectors. This one has coordinates delta u 0. This one has 0 delta v. And you exploit linearity. What do I mean by that? Well, so here L is that limiting linear transformation. So for example here, L might look a bit like this, but if you zoomed in even more, like times 1,000, times a million, times a billion, what is that approach? So because of linearity, we use a scaling property here. L of delta u times 0 is delta u times L of 1, 0. In other words, the place where delta u 0 lands after the transformation is delta u times the place where 1, 0, i.e. I hat, lands after the transformation. So if you want to figure out where I hat lands, you just divide by delta u. So let's say, okay, we've got that equation for the transformation uv goes to f1 of uv, f2 of uv. And when we apply that near here, this vector is a tiny change to f1 when you hold v constant. Remember here, this was just changing u, not changing v. And a tiny change to f2, the y component of the output, again when holding v constant. And similarly here, it's trying to change the f1 when holding u constant, trying to change the f2 when holding u constant as well. So when you substitute that in, you get this equality. And again, it's not technically an equality, but it's approximation. Again, we're at a finite zoom level here, zoom times 500. So zooming in more, so times 1,000, times a million, times a billion, corresponds to taking smaller and smaller delta u. And as you do that, that approaches this matrix of partial derivatives, partial f1, partial u, and partial f2, partial u. Because that's, okay, the change in F1 when holding V constant over the change in U, taking change in U to U0, that's just a partial derivative. And then it really is an equality. Like how before we just changed it to differentials to make an inequality. So the matrix representing the transformation is this matrix of partial derivatives. Partial F1, partial U, partial F2, partial U, partial F1, partial V, partial F2, partial V. And that's called the Jacobian matrix. So in this particular case, the transformation was UV goes to U plus sine of V, and V plus sine of U. So if you compute the Jacobian for that, it has components 1, cosine V, cosine U, and 1. So if you remember, we were zoomed in near 1.5 and negative 0.5. If you actually plug in those values, you get this matrix. And if we apply the transformation at the zoom level times 500, well, that's pretty accurate, right? So the x component of the green vector is about 1 times the original place. The y component is slightly more than 0. And for the red vector, its s component is just slightly less than 1. Its y component looks still to be 1. So this really is the matrix representing that linear transformation. So just like before, when we were looking at the local width distortion factor, here we want the local area distortion factor. We get that by taking the determinant of that Jacobian matrix, or I guess technically the absolute values if you don't care about orientation for area intervals. So this is the transformation law. du dv goes to mod of absolute value of the determinant of the Jacobian times du dv, which is dx dy. And that's just, so we've got area there, that's the correct area. Here we've got the local area distortion factor. And that's just the 2D change of variance. Right. So now let's see how to extend this to generalized surface intervals. For a surface interval, we still have a notion of an area element. In that case, that's filled by ds. And we have this mapping, x, y, z, as functions of u, v here. For example, you could write a sphere as r cosine theta, r sine theta, cosine phi, r sine theta, sine phi, and r cosine theta. And again, it's generally non-linear. But it has this property of local linearity. So again, I'm doing a particular non-linear transformation to the plane, and I'm zooming in closer and closer. And it looks more and more like it ends up being parallel and evenly spaced. And again, what we want to find out for that correction factor is the local area distortion factor. In this case, our Jacobian is a rectangular one. So we've got partial F1 partial U, F2 partial U, and also F3 partial. There's a 3x2 matrix. And how do we figure out the local area distortion factor of a 3x2 matrix? Well, we use the Gramian. So what you have is that du dv goes to the square root of the determinant of j transpose j times du dv, which becomes the area element ds. So this formula is the general surface interval formula. We do square root determinant of j transpose j. So for example, for a line interval, the Jacobian matrix is just x prime of t. So here you'd have square root determinant of x prime of t transpose x prime of t. So that's just a dot product. It's just the length squared. The length. And that's the line interval formula. For a surface interval, the Jacobian would be partial x partial u, partial x partial v. So this is what this formula says. But if you remember before, we showed that computing area using the cross product, using the Gramian, were the same thing. So that's the same as the regular surface integral formula. And okay, if you're doing change of variables, then J is a square matrix, right? So what you can do is split up this into det J transpose J, det J transpose times det J, which is square root of det J squared, which is absolute value of det J, which is the change of variables formula. This is actually the general formula for doing integration where you parameterize a surface in terms of some other variables u1 up to un. Square root of determinant of J transpose J, where J is the Jacobian matrix of that transformation. Right, that is the talk, pretty much. Just some final remarks. I've made like an Anki starter pack for this talk, which has some Anki cards on topics covered in this talk. I'll put the link in chat after I share on the screen. If you want to know more about Anki, there's this thing called the 20 rules of formulating knowledge. This gives some more advice for making cards. Like for example, the principle of atomicity is one of the 20 rules. Andy Matushak also has some good notes on this. All the animations here were made using Manim Community Edition. So Manim is the animation engine that 3v1 Brown uses. And then some developers forked it into a community edition, which is made by a team of developers. There are actually a ton of different applications of the Gramian that I haven't managed to touch on. Use it for solving these square systems, use it for finding the singular value decomposition, a bunch of different things. And all the study references here were mainly from Make It Stick, and also that augmenting long-term memory essay by Michael Nielsen. All right, that is the talk.
How long did it take you to learn Manim?
Oh, so okay. I think I started making this like 3 weeks ago. And like 3 weeks ago, I hadn't touched any Manim before.
Right, yes.
So just like learn more of that there.
Yeah. Nice.
Yeah. Actually, so I can check. It's about 5,000 lines of code for the whole talk. I think like there is a bunch of spaghetti code there. Like, I could have like cut it down maybe like 20%, maybe like 4,000 lines of code, but it's like a lot of effort went into this talk.
Like, what an honor! Thank you for putting so much effort in. Also, like the first part of the talk was surprisingly relevant to one of the part 3 courses I've just been revising on the statistics side.
Oh, okay.
So thank you. Modern statistical methods is all about using kernel methods to save some computation. Quick question. In terms of using Anki for maths, do you have any like particular recommendations other than maybe like focusing on explanations? Something I've really struggled to actually get working myself.
Right. Let me think. I think just really do try to keep an open mind about the things you're putting into Anki. Like the things I put into Anki like are quite different from like what you normally do in like conventional flashcards, like definitions and stuff. So like just keep an open mind. I think is some good advice there. Also be willing to change your cards. Like so I keep my cards in Obsidian, for example, and I use my plugin. So I can edit them very quickly because that's the same as editing my notes. So if I like see a proof and I see, okay, wait, this doesn't really make sense, I can just go and quickly change it and I can have a better understanding of that proof. Or if someone gives me like, okay, here's another way to prove the same thing, I think, okay, wow, that's a much better way. I'll usually like, okay, I'll delete the old cards and add those new cards and just update my understanding that way because I want to remember it for later on.
Sounds like the plugin's quite useful.
Yeah. I'll just post that link in the chat. Okay, so Ewan asks, I'm interested in Anki Obsidian in particular. What do the atomic cards look like within Obsidian? Okay, I guess I could like try sharing my screen again, potentially. And for example, if I look at the dimension theorem, this is what it looks like. So like if you look in the edit mode, it has like all these IDs and stuff, which if you copy these, you can actually find the cards in Anki. but they're all in HTML comments, so they all get commented out when you do it. Like that. It also has like links and stuff, which is very nice. And you might have also seen, like, also on the presentation, some of my cards had links on there. So because Obsidian supports hyperlinks and stuff. So if I click that link in Anki, it'll take me to the corresponding note in Obsidian, which is nice. I also have this Obsidian thing, which takes me to the note which created the card. So I can edit it easily.
Quite generally, there's a tendency for people who like maths to have sort of like a hatred of memorization in some sort of quite deep way, which is definitely noticeable. So what's sort of your response to that category of criticism?
So the way I like to think about it is that it's not just like rote learning where you're just memorizing all the definitions and stuff like that. Much easier to memorize something if you actually understand it, right? That's why I put explanations into Anki, because that way I actually understand the material. And if someone says, okay, wait, how do you actually know you're understanding it as opposed to just learning the explanations heart by heart? Well, I'd say to them, okay, ask me to explain the material. And if I can explain it, then doesn't that mean I understand it? Or if I can answer practice questions on it, doesn't that mean I understand it? At what point would you finally say, okay, you probably understand the material? Yeah, that's what I think. Like, if I just put like all the proofs and stuff into Anki without trying to understand them before, it would make my review sessions much harder. And that'll be more annoying. I don't like things being annoying. So I try to make things as easy as possible.
Well, what about the argument for if you, for example, lost all of your Anki stuff? Hypothetically, obviously you could back it up or whatever, but like, then if you've tied your knowledge base to being in Anki, and then
I've also had my notes in
Obsidian.
Obsidian. So if I really needed to, I could like go read through them in Obsidian and just like do regular rereading and stuff if I needed to.
No, I mean more like the criticism where if you use something like Anki religiously, then it becomes like a crutch.
Right.
Do you know what I mean? Where you're only going to remember things if you repeatedly see them in your card review sessions rather than just naturally just remembering stuff, I guess.
I mean, yeah, I guess like I still remember stuff outside of Anki. I don't put everything into Anki, for example. But I just find that like it makes it much easier to. Like if I didn't put it into Anki, I'd be like much more likely to forget. It's like a useful tool. Like how like people say, okay, writing notes down helps you remember them better because you're actually putting the effort in. Like, okay, is the notes now a crutch for you to remembering and you wouldn't be able to remember about the notes? Maybe, but it's just you using a tool.
My last question is, so what do your review sessions look like? I don't know if you already said this, and maybe I just...
So basically the way it works is that Anki will show you a card, which has like a front and a back, and you just try to remember what the missing information on the back is. You tap it, and it provides that information. And then there's 4 options to choose from. Again, hard, good, and easy. So again means like, okay, you got it wrong, and you want to like remember it again. So you reset the interval. Hard means that, okay, you got it right, but it took quite a while for you to get it right. So what that will do is that it won't reset the interval, but it will reduce the multiply. You'll see it a bit more often. Good is just a good thing, but okay, interval times multiply, nothing special. And easy means you find it very easy. So your multiply will get a boost. So I just like go through cards. I think like in term time, it amounts to about like 30 minutes a day on average, and holiday time like much less.
Do you write things down while you do it? Because I remember when I used to use...
That'll take way too long.
When I used to use it for like school, like, you know, before uni, it would be like I'd have a piece of paper and I'd practice writing stuff out when it came up, just because otherwise it's not... Yeah, you can sort of think that you remember the whole definition, but you don't actually when you go to write it out.
I don't know, my experience has been like, if I have been seeing an Anki a bunch, then I can usually recall it quite quickly. Like I've had in supervisions, for example, where my supervisor asked, okay, do you remember the proof of the X and Y theorem? I was like, oh yeah, that's very easy. I mean, if you want, you can just think of Anki as, okay, revising little and often is a good idea, right? And Anki provides a good way to implement that, even if you don't want to buy into the whole spaced repetition, testing effects, stuff like that. If like, because like for me, for example, I just found it very tedious to try to make a whole revision schedule for everything. You know how we're told, okay, you should be revising over your previous lecture notes when you're doing lectures and stuff like that. But I never could actually figure out a proper schedule for that. I just use Anki to manage all that. Because all I have to do is, okay, I do the calls for the debate, and then I'm done. I don't have to worry about anything else. There's a revision.
Cool. So thanks so much for giving this talk, and thanks to everyone who showed up to this talk. This was a very interesting talk, and I'm sure we all, like, given the amount of questions, we can see we all are quite interested in this method of using Anki to learn math. So thanks again for giving the talk, and I guess we'll end here now.